Okay, so I'm continuing the worksheet. We left up on number 8, and I'm going to go ahead and get started. So on problems 8 through 9, use the definition of continuity to find the values of k or m that will make the function continuous everywhere. So we have to use the definition, and recall that the definition has 3 conditions. F of c must exist, the limit must exist, and the limit and the function must be the same value. So let's go ahead and test this over here. So this is number 8. So we want to go ahead and test if the function value exists. Well, why am I choosing 2? Well, I'm choosing 2 because we have a piecewise function. We have a quadratic on what appears to be the left side of 2 and a linear on the right side of 2. So we want to determine if this function that's broken into 2 pieces connects or it doesn't connect. Well, the instructions already say we need to find the continuous function, so we just need to find the k that makes the functions continuous. In other words, we need to find the k value that will make these functions meet at a certain point. Well, we don't have to test condition number 1 because of this equal sign here. It says that the function already exists at 2. We just don't know what it is, because if I plug it in, I get k 2 squared, which is just 4k. I don't know what that is, and we'll find out what that is. So it does pass condition number 1, because if I were to plug in a k value, I get a value for my f of 2. The second condition says the limit must exist. Recall that the limit exists only if the left-hand limit and the right-hand limit are equal to each other. So that means that if x approaches 2 from the left of f of x, and x approaches 2 from the right of f of x, these two values must be the same. So let's go ahead and figure it out. If I substitute 2 on the left side of the equation, I get k 2 squared, which is 4k. If I do the same for the right, I get 2 times 2 plus k, which is 4 plus k. Now, according to continuity, the limit must exist, which means that these two must be the same. So we can equalize them, and we can solve for k. So that gives me 4 is equal to 3k, and 4 over 3 is k. So I just found my answer. I found the k value that will make this piecewise function continuous. So how do we check it? Okay, well, we check it by plugging in the k value into each of these k's, and then plugging in the 2 into the x's. And if both sides of the piecewise function were to give me the same value, then that is sufficient amount of information for me to say the function meets at this point and is continuous from the left and from the right. So let's do the check. So plugging in on the top the k, and then the x value will give me 4 thirds times 4, which is 16 thirds. Now from the right value, the right side, which is the linear function. So it's going to be 2 times 2 plus 4 thirds, which is 4 plus 4 thirds. The same thing as 12 over 3 plus 4 thirds, and that is 16 thirds. So these two are the same, and that's how you check your work. Okay, problems 10 through 12. A function f and a closed interval a to b are given. Show whether the conditions of the intermediate value theorem for the given value of k. If the conditions hold, find a number c such that f of c is equal to k. If the theorem does not hold, give the reason. Whether the theorem holds or not, sketch the curve and the line y equals k. So I'm going to go ahead and choose to do number 11. So recall that the IVT is simply just a fancy way of saying um, if you have a closed interval, a function on the closed interval a to b, and it's continuous, then all the other points inside the continuous function from a to b are defined, and they all pass continuity. So let's go ahead and check this. So let me go ahead and paste this somewhere else. Okay. Okay, so the way you check this, okay, so we want to determine if this y value of 3 is inside the interval when I plug it in into my x values. Okay, so let's check this. So it's going to be f of negative 4.5, which is the same thing as 25 minus negative 4.5 squared, and then f of 3, which is 25 minus 3 squared. Okay, so I get 25, take away a 20.25, and 25 take away a 9. So that must mean that I have a square root of 4.75 and a square root of 16. This is 4, and I don't know what the square root of 4.75 is. I can say that the square root of 4 is 2, the square root of 9 is 3. Since 4.75 is closer to 2, I can say that it's about 2 something. Okay, so, well, it doesn't matter what it is. All we want to do is test to see if this y value, if 3 is in between f of negative 4.5 and f of 3. Is that true? Well, let's see. The square root of 4.75, which we said it was 2-ish, is 3 in between these numbers? Oops. That was 4. Well, yes it is. 3 is in between a number that has a 2 and 4. So, f of x well, let me rewrite this. So k equals 3 satisfies the IVT for f of x since f of negative 4.5 is less than or equal to 3, which is less than or equal to f of 3. And that's it. Pretty much what we're saying is we're just saying a fancy way that 3 falls in between these two y values. So the theorem satisfies this problem for f of x. Okay, and the last problem, we have a quadratic function, and we want to determine if f of 7 is somewhere in this interval for this quadratic. So very simple test. F of negative 1, which gives me a 1, minus 2, minus 5, and that is a negative 6. And f of 3, that is 9 plus 6 minus 5, and that is 10. f of x is equal to 7, which is, well, pretty much just y. Y is equal to 7. Does y equal to 7 fall in between these two y values? And yes, it does. So it does, and we use the intermediate value theorem by testing the endpoints of the interval. And letter B is pretty much the same, except that we have now a different value. We have, for part B, y is equal to 12, and we see that it does not fall inside the value of -6 and 10. So for part B, we have the intermediate value theorem that fails. So since f of -1 is equal to, what did we say it was, -6, and f of 3 is equal to 10, there is no x, or we should say there is no value x equals c such that f of c is 12 in the interval from -1 to 3. And that would be a good explanation of why intermediate value theorem does not hold for this problem.